Hypothesis test for mu, sigma known, video 3. As I started this video, it dawned on me that I left an open thought in a previous video about under what circumstances would you want a stronger significance level. An example is escaping me right now, so hopefully I'll run across one between now and the end. But I'll tell you right now that in your homework, you will be told what significance level to use. So for now, you won't have to worry about determining one. All right, let's get down to it. I'm going to show you how to test mu, test a population mean. Now this is called the critical value approach. There's actually two approaches I'm going to show you. They're somewhat similar. One of them just makes the decision in a different light than the other, but they have some similarities in their steps. In general, and I'll elaborate on these steps, here's our 5 steps. You'll notice I left some space after number 3 because I'm going to write a formula there. Step number 1, state the hypotheses. Okay, that stands to reason. Just remember, they must be about the population parameter, not about a sample variable. So you never state a hypothesis about X bar or P hat. You can state a hypothesis about mu or P, because those are population parameters. Step 2, sketch the critical regions. This is what was illustrated in the previous 2 videos. Determine the critical values. So we're going to use the Z table. 3, calculate the test statistic. I'll write a formula here in a minute, but this 3rd step is going to take the sample evidence and turn it into something that we can compare to the critical values. And based on where it lands, whether a critical region or not, we will draw a conclusion, make a decision about the null hypothesis. And if we're in the context of a word problem, and most of the time you are, answer the question in context because there's usually a question to answer. So let's take a look at this example and go through all 5 steps. A restaurant claims the average tip for its wait staff is $5. A sample of n equals 87 tips yields a sample mean of $4.50. That's contradicting what the restaurant claims. We're going to test at alpha equals 5% the significance level if the population mean is actually less than $5, because our evidence suggests that. We're going to assume that the population standard deviation, this was supposed to be 25. Well, we could do it with 5, and if I remember, at the end, we might ponder what would happen if this were 5. But remember, in this section, we're assuming that we know the population standard deviation. Is there enough evidence to conclude the average tip is less than $5? I know the evidence suggests it, but is it enough evidence? All right, let's go through the 5 steps. Step 1, state the hypotheses. Okay? Remember, when you state the hypotheses, they occur in pairs. Null hypothesis, alternative hypothesis. They are always about a population parameter, in this case about mu, which is kind of clear from the title of the section. Our book will always use equal in the null hypothesis. The restaurant claims that the average is equal to $5. But what would the alternative be? Well, it's right there. That the average is less than $5. If you're wondering why can't we put that the average is equal to $4.50? Because the null hypothesis never discusses things being equal. It just discusses things being different than what the null claims. I think I said null a minute ago. The alternative hypothesis never allows this to be equal. The purpose of it is to contradict what the null is claiming, and the null is claiming equal. All right, so there's our hypotheses. For the 2nd step, we're going to sketch the critical region or regions and determine the critical value or values. The reason I keep saying singular and plural is the number of regions and the number of values depends on the type of test. So it's critical that your alternative hypothesis is correct so that you can correctly identify this as a left-tailed test. You're in the garbage. Oh man, it bounced off the wall. So this is going to be a left-tailed test. Now remember what that means. On our bell curve, we cut off a left tail. The significance level represents the area of that tail, and since the significance level was 5%, that means that this area is 0.05, but for z-chart purposes, we'll put 2 more zeros on it. And we had looked up that area previously. It was dead center between 2 z's, and the one we went with was negative 1.65. Technically, you should label this as the critical region. At the very minimum, you need to recognize that it's the critical region. But if you ever end up doing statistics for a work-related thing, you don't want to leave anything subject to misinterpretation. So labeling it as the critical region would be a way to do that, to not leave it subject to misinterpretation. All right, so the second step is basically draw the picture, cut off the tail with the correct area, and find the z. Pretty straightforward. Step 3, calculate the test statistic. All right, this is just a formula. In a nutshell, what we're about to do is take what our sample gave us and turn it into something that we can compare here. Right now it's apples and oranges. This is an x bar, that's a z. But we've converted x bars to z's before. In fact, it's the exact same formula. The formula for the test statistic is z equals the x bar that we get from the mean minus, I'm going to write mu subscripted with a 0, and I'll explain what that means in just a second, divided by sigma sub x bar, where sigma sub x bar equals sigma over the square root of n. The mu subscripted with the 0, first let me check to see if the author uses that notation as well. As I mentioned before, notations in statistics is rarely consistent. He does. Although in the formula in the book, they don't pause and call this sigma sub x bar, they just take this fraction and cram it under there. I don't like doing that. But what this mu sub 0 represents, this is the hypothesized value of mu. And the reason it's subscripted with the 0 is because you look in the null hypothesis to locate that. So basically it's what your sample is minus what you're claiming about the population. So we got a little bit of work to do for step 3, but it is just a little bit of work. First we need to figure out the denominator, sigma sub x bar. That would just be the standard deviation, which is 25, divided by the square root of the sample size, square root of 87. This will not come out cleanly, so we'll take it to 4 decimal places. You can almost never go wrong if you use 4 decimal places. You rarely need more. They may ask you for fewer, in which case you can round off later. So we get approximately 9, that's not right, that can't possibly be 9 something. 25 divided by the square root of 87, oh I forgot to press equals. 2.6803. Now that's not our test statistic, that's the denominator of the formula to calculate the test statistic. So the test statistic, I'm just going to write test stat, is z equals what we got from our sample, which was $4.50, minus what they're claiming in the null hypothesis, $5, divided by the standard deviation of the x bars that we just calculated, 2.6083. And if we put that into the calculator, be careful, you have a subtraction problem and a fraction, so if you're going to put it all in one fell swoop, you have to put parentheses around the numerator. Parentheses, $4.50 minus $5, close parentheses, divided by 2.6803. And we get a value of negative 0.1865. So this is what's called the test statistic. This is the value of z that we got from our sample that we're going to test against the critical value. Now we just have to do a comparison. To draw a conclusion, all you have to do is locate your test statistic back over here in the picture of your critical region. Remember, we're doing z's in this picture, so the middle is 0. So where would negative 0.1865 land between in this picture? And the answer is to the left of 0, but not this far left. So the test statistic would be about here, negative 0.1865. It did not fall into the critical region. This is how you make your decision about the null hypothesis. If your test statistic crosses over into the critical region, you reject the null hypothesis. If the test statistic does not cross over into the critical region, you do not reject the null hypothesis. I much prefer calling this the rejection region and the rest of it the non-rejection region, because its name tells you what to do. This test statistic stays in the non-rejection region, so our conclusion is do not reject the null hypothesis. Do not reject the null hypothesis. But our sample gave us $4.50 and that's less than $5. I'm not disagreeing with that. What I'm saying is the discrepancy is not blamed on the fact that the null hypothesis is wrong. It's blamed on the fact that this particular sample gave us $4.50. Had this given us a much lesser value, like $1.50, then maybe it would have fell over here. Or if the sample size were much larger, what would the effect of a larger sample size be? A larger number here would mean a smaller number for the sigma sub x bar. Smaller number here means larger number for the z. So pick a bigger sample. But the law of large numbers says that as you pick larger and larger samples, you get closer to the true value for the population. So our test statistic landed in it did not land in the critical region, so we don't reject the null hypothesis, and now we answer the question. Is there enough evidence to conclude the average tip is less than $5? In other words, was there enough evidence to conclude the alternative hypothesis? Well, if we don't reject the null hypothesis, that basically means we're keeping it and not the alternative. So no, there was not enough evidence. And again, we're not saying that this means the average tip was $5. We're saying that the evidence isn't strong enough to reject that claim. The average tip could be less than $5. We just don't have enough evidence to draw that conclusion. I know this was a long video. I'm afraid to look over and see how long it's gone. 13 minutes. I've seen longer videos. But being the first example of testing a population mean using the critical value approach, I think it was, pardon the pun, critical to take that much time. So let's just quickly review what happened. You state the hypotheses, done. You sketch the critical regions and determine the critical values, translation. Draw a bell curve, cut off the correct tails according to the alternative hypothesis. Assign the significance level as the area of the tail or tails, and use the z-chart to find the values that separate the tails. The tails are called the critical regions. The z-values are called the critical values. Your third step is to convert what your sample gave you into a z-score. That's just an old formula. First find the sigma sub x bar and then convert the x bar to a z. Then you just compare your test statistic to your critical value. If it crosses beyond and goes into the tail, into their critical region, you reject the null, otherwise you do not. And then answer your question. We'll take a look at another example. This one will go a little bit more smoothly. And one other thing that I meant to mention at the beginning of video 1 in the series, we still have one more series of videos to do, hypothesis test for P, but that will go a lot more quickly because the flow is just like this. All we have to do is change some formulas. So long videos now, short videos later.